Today's topic is improper integral. So what is an improper integral? You see that infinity right there? That's improper integral, okay? And do you see that this answer is infinity, or is it obvious, or is it not that obvious? There's your first question. Okay, I have this thing graphed. This is 1 over x, so this is not 1 over x. I'm gonna delete this, and this is 1 over x, right? So starting from here and all the way to the infinity. Is that infinity? If you have infinite interval, that area, does that give you infinite area? You want me to evaluate it? Yeah, let's evaluate that. Okay, so and hopefully this computer will behave. Okay. Let's see. So what we are looking at is this area right here, and this infinite area, right? All the way here. Now this is how you are supposed to evaluate infinite integral. 1 through infinity, 1 over x dx, right? You cannot be substituting infinities around, especially this period. Those of you who never listen to anything I say, once you start substituting infinities, it's automatic 0 on my test, on the AP, everywhere, okay? Infinity is not a number, it's an expression. Or the problem is written this way, you are not allowed to do such a thing, okay? Listen to the instruction. So this is the very first thing you do. You have to rewrite it as a limit from 1 through b, and b will approach infinity. Concept of that is this. Let's cut it somewhere here and call this thing b, and it's this area we're computing, but this b will approach infinity. You know what I'm saying? It is similar concept as this 0.3 repeating. Is it equal to 1/3? Did we talk about that?
Not
are they equal or are they not equal? Wait, we never talked about this? Let's talk about it. Okay, this versus okay, this thing, 0.9 repeating, is it equal to 1? Or is it slightly short? Well, those of you who don't think this is not exactly equal, what about this now? Are they exactly equal? Yeah, because that's you learn how to convert fraction to decimal in elementary school, hopefully, right? But what happens if you multiply both sides of this equation by 3? And then you get that. Whoa, you want to change your answer now? They're the same thing. Either they are both exactly equal or they're neither exactly equal. So which way is it? Hold your thought. Because there's this little book that I had to do summer assignment in my elementary school, out of all places. I know I went to an amazing elementary school. And they tried to convince me by doing this. I mean, they tried to convince me that they are the same thing by doing this. Oh, 1 minus 0.9 repeating is equal to 0, so these two must be equal. Aren't you convinced more than ever that they are not equal now? Like 1, there's a 1, where is that 1? Well, that 1 is infinitely far away, right? So, are they equal or are they not equal? I want answers now. Or should we vote and let the democracy decide? thing about the truth, stubborn thing about truths or fact is that truth does not care how you feel about it, right? If nobody agrees with it, it's still truth. You know what I'm saying? It's just the general population might be misguided. Truth does not care about opinions or feelings. You see the classic difference between the conservatives and liberal. Okay, let's not get there. So they are not equal. So what the heck do we mean by this thing? Sometimes the equal sign is used loosely or liberally to drive a point in mathematics, and it's regrettable. This is a concept of a limit. They are approaching this number. So this is really a geometric series, and we're going to learn about it in series chapter 9. This series converges to that number. You get it? It is a concept of our good old limit. This series converges to that number. That's all that means. Okay, so they're not equal, although we write equal sign, because when we say limit, it means not equal to in the first place. You know what I'm saying? Okay, so that's how we mean. So we'll come back to our little problem here, okay? That integral sign looks ugly. Really. So we evaluate this from 1 to b, and b will approach infinity, okay? Now, and then we write 1 over x and dx. Okay, that will be equal to limit as b approaching infinity of, this is ln, right? Are we sure? Because you still don't want to write ln unless you're sure. So are you sure? Negative 10 still applies. Okay, now this is equal to, we substitute, so we have still limit, and you have to of course carry this limit everywhere on every line. B approaching infinity of, so we have ln b. Oh, by the way, why do I not have absolute value around ln? Because the antiderivative of 1 over x is ln absolute value of x. Somebody answer that question.
Because it goes from 1 to positive infinity. Always
very good, right? Our interval x is always positive within this problem, okay? Okay, and then ln1 is equal to 0, right? So what you see is this is 0, but this thing approaches infinity now. It approaches infinity but not equal to, you get it? So we get infinity as our answer. How about that? Good. Okay. So this top one is obviously infinity. But what about this one? Is that also infinity then? I'm going to graph that one. I'm going to superimpose it on top of this. So this is our previous one, this area, which turned out to be infinity. And this is my new one. Well, there's that gap. But this is infinitely long, so shouldn't that be infinity as well? What do you say? Well, one way to find that out is graphing calculator, right? Okay, I already did it because when I tell you to do it, then you can just stare at the screen. Oh, yeah, you do it, right? So I did it already. There. What? That's tiny compared to the previous one, which is infinity. I mean, this is like literally difference between heaven and earth. You get, I only went up to 1,000 because this thing takes its time, but do you get a feeling that your answer should be 1? How do we read that expression if this is equal to 1? It's not equal to 1, but by the way, it's exactly same as. So this improper integral converges to 1 is how we want to say it, right? It's a concept of convergence. Remember that series, infinite series last year? We have an infinite series chapter, which is a month long. So it's a matter of convergence. Okay, we will evaluate that by hand. So I'm going to delete this one now and copy this. Okay. Okay, and then push the other example down. Okay. Now, so our example, which I'm going to do in blue, is 1 over x squared now, dx. Okay? Starting from 1 all the way to infinity. So that concept is, once again, here's 1. And instead of evaluating, substituting infinity, I cut it somewhere here, call that b. And that b will approach infinity, so that area. Okay, and we expect 1 to be our answer. Okay, so first thing we do, we rewrite this into proper integral, which is b approaching infinity and 1 to b, and might as well write it like that, right? Good. Okay, then this thingy will be limit of b approaching infinity of, is it x to the -1 power, therefore minus sign here, right? 1 to b. And then, now we substitute. Should we use plumbing, professor, this minus that one because of that negative sign? So we say 1 minus 1 over b. Too much algebra? You got it? Who's confused? Let me know right now. Negative of 1 over b minus -1. You know what I'm saying? Okay. And then, once you evaluate the limit, this thing dies, right? So we have 1, as we expected. How about that? Okay, so this area is equal to 1. And, whoa. Let's compare the answers to the previous one. This area is infinity. This area is 1. Good. Okay, well then I have this question. We want to evaluate this. What does that look like? Wait, is it even improper integral? Do you see? There's a sneaky, this is a sneaky problem. There's an improper integral hidden inside. It's not as obvious because you don't see that infinity. Okay, I'm gonna put it on graph. Okay, I'm gonna delete this. This part right there. Okay, I'm gonna copy that. So this time we're cutting still here, but all that area that way. Now, can you tell what that area should be by comparing this answer to that answer? Look at the shape. This thing versus this thing. What should be our answer here? What do you expect? Somebody brilliantly suggest. Symmetry is kind of striking now, isn't it? This shape stretching all the way to infinity. Compare that to this shape stretching all the way to infinity.
Is it?
Okay. 2. Somebody said 2, right? 2 is correct. Why is 2 correct? If you think about it, this area right here looks exactly same as from here, that area right there, doesn't it? And then area of this square is literally 1. You know what I'm saying? So you see, here's a vertical asymptote. That's sneaking right inside, right? Remember our fundamental theorem of calculus fails when the function is not nice. It only works for well-behaved functions. So what is the classic prime example of not so well-behaved function? Mathematicians throw these like fancy word like singularity around here. This is what they call singularities. Denominator becoming 0, right? Vertical asymptote for us. Oh, and that's like if there is a vertical asymptote anywhere between these two, or even at the end, that makes this thing improper integral. This may or may not converge. We don't know. In this case, we expect it to converge to 2. Okay, so how should we evaluate this one, right? So scratch this idea. This is a better concept. We'll still draw this line, say vertically right there. That's nice, right? This computer is just giving me so much trouble. Like that, and we'll call that A. And we'll compute this area right here. But this A will take a limit and bring it infinitely close to 0 from the right-hand side. You get the concept? Okay, so let's take this integral. So from 0 to 1, 1 over square root x dx. The way you rewrite it into proper integral, first thing you do is A approaching 0 from the right-hand side, and from A to 1 is the very first thing you do before you do anything. Good? And then might as well rewrite this as x to the negative 1/2 power dx. Are we good? And A approaching 0. And that, of course, is x to the positive 1/2 power, therefore 2. And from A to 1. Let's take that 2 out, since it's constant to the front. So A approaching 0. And then we'll substitute 1. So we have 1 to the 1/2 power minus A to the 1/2 power, right? Square root A. Now we take a limit and A approaches 0, so this dies. So we have 2 as our answer. How about that? You get it? Ah, that was more sneaky improper integral, which you're responsible to know. And then there might be a vertical asymptote in the middle of the interval, and you have to break it up into 2 separate integrals. You get it? Okay, well then. Let's take this example. Well, this case. Evaluate this integral, let's say. What happens if we have this kind of situation? There's function. And then we have this negative infinity and positive infinity. How are we going to write the proper integral? Because we have an improper side on both ends, right? And you don't write this because this is incorrect. You might wanna this very tempting, right? You write A approaching infinity, and then you put negative A, positive A, so both end approaches infinity. You know what I'm saying? This is tempting, isn't it? No, you don't. This is wrong. Why is it wrong? Because many times this integral, one side will converge and the other side will diverge. So you cannot really have it like this, unless the graph is exactly symmetrical. Unless we have an exact even function, cannot do such a thing. You know what I'm saying? So no, can't do that. Okay, then, okay, fine. Then this is another tempting. A, B, have A approaches negative infinity and B approach positive infinity, double limit. How's that? I wish they invented this notation in math, but unfortunately they did not. So nope, can't do that either. Dang it, right? So what is the only proper way of doing this? You have to break this, and 0 is a nice breaking point, but you don't have to break it at 0. Most people like 0. One piece plus, and then you have to have another piece. Limit of b approaching positive infinity from 0 to b of f of x dx, like that. This is the only way you can do this. Okay, let's take this example. Say we have negative infinity to positive infinity of e to the negative absolute value of x dx. Do you know what this thing looks like? Okay, I'm gonna make it right here with my other computer. This thing looks like this. Oh, it's at least symmetrical, so we can use symmetry, right? It's the ultimate even function. Absolute value is the ultimate even function, right? So it should work out nicely, but suppose you can't see that. So we'll just muscle it through. So way you want to convert this into proper integral is limit, and this is a to 0, and a will approach negative infinity. And that's e to the, how do you rewrite piecewise function into, the absolute value function into piecewise? This is negative and negative x, like that, right? That's the left-hand side. And plus limit as b approaching positive infinity and from 0 to b and e to the negative x dx. Do you see how that thing breaks up? Who's confused? Let me know right now before I move on. Okay then. So this one, limit a approaching negative infinity. Now that's just e to the x, so antiderivative is e to the x. And from a to 0 plus the other piece, b approaching infinity. And that's e to the negative x, so with a negative sign here, and 0 to b. With me? Okay, substitute. So e to the 0 is 1 minus e to the a plus limit b approaching infinity of, use plumbing professor, that negative sign, right? So this one first, so 1 minus e to the negative b. With me? Okay. And if we take a limit as a approaches negative infinity, so this thing dies. And this b approaches infinity, so this is negative sign here, so this thing dies. So our answer is 1 plus 1, which is equal to 2. Shall we? So that is limit. And improper side is here at the lower limit, so I'll write that as a to 0, and then have a approaches negative infinity. So far so good? Okay, now then we write x squared e to the x and dx. So far with me? Zoom in a little bit. Now, this is a lot of headache to just keep write these things with, this is integration by parts, isn't it? And this is a lot of headaches, so what I usually do is do that part on a side. So I'm going to do that integration by part here on a side. Okay, so if I have integral of x squared e to the x dx, my u is x squared, and my dv is equal to the e to the x dx, right? And then du is 2x squared, and v of dx, I always forget that little thing, But then when you forget, I never forget to deduct points. It's amazing how that works, right? I know. And this is still e to the x. So this integral turns out to be uv, these two, so x squared e to the x, and then minus the integral of these two. So we have 2x e to the x dx. And we do this one more time, and looking like I'm going to need more space, so I'm going to move that to the side a little bit. And then I do u is now negative 2x. Get it? Including the sign and all of that. Oh, by the way, so this chapter includes all of the techniques of integration from chapter 6 and on, right? You see how this test will turn out? Yeah. Okay. And then dv is still e to the x dx. So du here is negative 2 dx now, right? Okay, and v here is e to the x. Now, before I forget, 1, 1, 1, 1, 2, 2, 2, 2 to make it perfect. So my integral x squared e to the x, now uv, so negative sign, right, is baked in already, so negative 2x e to the x, and then minus the integral of these two. So that negative sign cancels this negative sign, so we have 2 e to the x dx. And integrating it, so we have x squared e to the x minus 2x e to the x plus 2 e to the x plus c. How about that? You got the integration part? Okay, now we can come back here. Whoa, I need a lot more space. So I'm going to shove everything to the right. One little good thing about this distance learning is we can control the board. Everything else is bad, but hey. So I have, oh, let me try copy and paste. It's another thing that's nice. Then paste it here, right? Look at that, huh? Change the color to red. And resize it a teeny bit. Yeah, that's perfect. Get rid of that plus. And then from A to 0. So far so good. Now we have limit of A approaching negative infinity. Now once you substitute 0, all of these things die except for that one. So we have 2. Good. So we have 2 minus, and then I substitute A, right? So here I have A squared e to the x. Good. Okay, plus minus 2a. A, that was A. Oh, it doesn't want to erase anymore. Uh-oh, don't tell me it's going to crash. Because that happened a couple of times in second period, and that recording was shot. Okay. E to the A plus 2 e to the A. So far so good. Now I have to take a limit. And when I take a limit, then this dies, right? Because A is approaching negative infinity, e to the negative infinity is 0. Our question is, what happened to these two? This is infinity times 0. So is this. How are you gonna figure this? We L'Hospitalize it. So I'm gonna do it on the side. I know, right? Okay. Let's do it this way. Limit of A squared. This will include the work for this one, so just watch. E to the A as A approaching infinity, right? I'm going to rewrite that as limit of A squared over e to the negative A as A approaching infinity. So far with me? Then we'll have limit of a approaching, oh, I said negative infinity, right? This is negative infinity. I'm going to zoom it a little bit and then insert negative infinity there. Oh, negative infinity. And then we L'Hopitalise it. So derivative to a over, this is negative a to the negative a, right? And then this is still infinity over infinity, isn't it? Because when a approaches negative infinity, right? So round 2, and this thingy is actually work for this part. You get it? Okay, so limit of a approaching negative infinity and 2 over another derivative, so we get this thingy back. So first of it, and now we can let a approach negative infinity, so that's 2 over infinity. So that's 0. How about that? You get it? Okay, so what we have here is this thing is 0 and this thing is 0. So finally, our final answer, we get 2. Good? Question? That's all of number 18. Let's do number 22. Okay, number 22, the graph looks like this. Wow, that looks symmetric. So do these all negative infinity area? This is negative, all of it. Does it cancel all of this positive area? Is the question. Do they? You have to be very careful when you answer that kind of question. They will only cancel if they are both convergent. Well, they are symmetric size. So if it's convergent, then they will cancel. If it's infinity minus infinity, generally infinities don't cancel. And there's a story to go with it with this professor from Stanford today. Later, I will tell you the story. So it's only true when they are convergent. Okay. In this case, they will turn out to be convergent. Okay. Alrighty. So let's do number 22. Okay. Now, do you realize this is a U-sub? Yeah. So we'll write it into proper integral first. So a approaching negative infinity from a to, let's break it up as 0, right? So we'll put 2x and e to the negative x squared dx. Okay. Say yes. Plus limit of a approaching positive, or b approaching positive infinity from 0 to b of 2x e to the negative x squared dx. Are you with me so far? Okay. Then, can we do the U-sub in our head, or do you want me to do it for you on the side? Who wants to see it on the side here? Okay, nobody. Limit a approaching negative infinity. This is just u, du. Negative sign is the only thing that's missing. You know what I'm saying? You know what I'm saying? Okay. If you're confused, now is the time. Okay. I see a hand. So yeah.
Well, if you do U-sub, wouldn't the exponent be u instead of negative x squared?
Well, that depends. If you can actually look at this as a u, and then when you take an antiderivative, you pick up negative sign, or you can look at all of that as u, and then adjust it with a negative sign. Both way actually works. But one thing you should do is when you try to do this in your head, we'll take a derivative and see if we get that back. Okay? So the derivative of this thing, wait, can you see my cursor? We'll do it this way. If you take a derivative of this thingy, then we get negative sign is there, e to the thingy, chain rule, negative x squared, so negative 2x will cancel, so we get that thing back. You know what I'm saying? Okay. So plus, and then limit of b approaching positive infinity, and it's the same thing. So negative e to the negative x squared from 0 to b. You with me so far? Okay, we evaluate the limits. So we have limit of a approaching. This is a lot of work, right? Once you substitute 0, should we use plumbing, professor, and do this minus that? Yeah. So substituting a first, e to the negative a squared minus substitute 0, so you get 1. Good. Okay, plus limit b approaching infinity. So we'll do plumbing, professor, here as well. Substitute 0 first, so you get 1 minus e to the negative b squared. Are you with me? Now, when you take a limit, see, this thing dies, right? Because this e to the negative infinity thing, because it's squared, and this thing dies, right? So we have -1 plus 1, which is 0. So since these things are convergent, and they are exact same shapes, so by symmetry, they die. So this is an odd function. So this odd function canceling each other still applies all the way to infinity, provided that these improper integrals converge. If they diverge, then bets are off. Good. Okay, then we'll get to number 23 then. Okay, 23, we have to tweak it just a little bit, okay? Now, so first, shall we rewrite this into proper integral? I think I'm going to resize this a little bit. Okay, so let's convert this into proper integral. So let's break it up at 0, as always. X approaches negative infinity from a to 0, and then dx over e to dx plus e to the negative x plus limit of b approaching positive infinity and 0 to b, and then we have dx over e to dx plus e to the negative x. So far with me? And then integrating this thing is pain in the butt, right? So I will do this on the side over here, okay? So let's do that with a different color. So antiderivative part now. This dx over e to dx plus e to the negative x. The trick here is we multiply e to dx here, here, here. E to dx here, here, here. Get it? So if you do that, then it becomes this. E to dx dx over e to the 2x plus, and this thing cancels and 1, right? Now, can you say what is the trick here then? This is a form of x squared plus 1. You know what I'm saying? So this is trig sub. But instead of letting x equal to tangent theta, we let e to the x be tangent theta. And this is like magic. Watch. So derivative both sides, we still have e to the x. dx is going to equal to secant squared theta d theta. So far so good? That part is good, right? Okay, now the denominator, this thingy, e to the 2x, e to the x quantity squared plus 1 is tangent squared plus 1, isn't it? And that also becomes secant squared theta. So we have this thingy over this thingy, right? So secants cancel, so we only get d theta, which of course is theta plus c. And our theta from here, now you have to be careful, that's the inverse tangent of e to the x. You get it? Plus c. You with me? Now we plug it in here and we can use it. So we continue here. Limit. See, this two-column approach works out really well for me over the years. So I highly, highly recommend it because your notebook is usually wide enough, right? So you can actually have this kind of work going back and forth. Okay, so A approaching negative infinity of our antiderivative, which is inverse tangent of e to the x, and then from A to 0. Good. And plus limit p approaching infinity of same thing, inverse tangent of e to the x, and from 0 to b. You with me? Okay, we'll substitute. So we have limit, zoom in tiny bit, a approaching negative infinity, substitute 0 first. This, don't be careful, be careful, don't be careless. It's not 0, it's not inverse tangent of 0. This is inverse tangent of e to the 1, e to the 0, isn't it? So this whole thing is inverse tangent of 1. What is inverse tangent of 1? See, I'm going to make a little notation. This becomes 1. You know what I'm saying? So what's the inverse tangent of 1? Somebody tell me.
Pi over 4.
Very good, thank you. So this becomes pi over 4, right? Minus inverse tangent of e to the a is what we have so far, plus limit of b approaching positive infinity, and then substitute b, so we have inverse tangent of e to the b. So far so good? Okay, minus, and likewise this will be pi over 4, wouldn't it? Say yes. Now we take the limit. When we take the limit, this thingy, inverse tangent of infinity. Ooh, what's that? What's the horizontal asymptote of inverse tangent? You want me to draw it for you? Oh no. Okay, inverse tangent looks like this. I'm gonna make it, I don't need all that thing. See, inverse tangent looks like this, doesn't? This computer is just great, isn't it? Inverse tangent looks like that, doesn't it? And this is pi over 2, and this is negative pi over 2. You know what I'm saying? So this thingy becomes pi over 2. Wait, that thingy doesn't become pi over 2. I meant this thingy become pi over 2. Good. Now this one, this approaches negative infinity. So e to the negative infinity is 0. So this thing is inverse tangent of 0, which approaches 0. You get it? This problem has many different things to consider and think about. So let's summarize. So we have pi over 4 minus 0. And then we have pi over 2. And then minus pi over